Problem 5, radiation. Prior to dressing for school, the student watches the morning weather to decide what to wear. The bedroom is 65 degrees and the student's skin is 94 degrees Fahrenheit. Already that's kind of stinky because we have to convert that. Determine the net energy transfer from the student's body during the 15 minutes spent watching the morning weather. Note, the skin's emissivity is 0.9 and the surface area of the student is 1.3 meters squared. All right. So, as before, we're going to write down our values. Okay, now this is a little different because we're doing radiation, so we don't really have an initial and a final. We're just trying to figure out how much energy gets transferred out. All right, so we're not raising or lowering any temperatures. We're just going to assume that the room is cooling off as fast as the student's body is heating it. So let's look at some of our values, and we're going to start running low on room here. So let's start with the easy one. Area A, 1.30 meters cubed. All right, the area of the student's skin. The emissivity, okay, they give that to you, is 0.90. That's E. All right, what else do we need? We know the bedroom temperature. We're going to call that, let's say, T1. That is 65 degrees Fahrenheit. Ugh, I hate that Fahrenheit. Skin temp, call that T2. That's equal to 91.4 degrees Fahrenheit. Okay. How long they're in the room, so time is 15 minutes, which is equal to 900 seconds. We know that. We also learned about, for radiation, Stefan's constant. Oops, spelled that wrong. Stefan's constant, all right, that is equal to 5.6696. By the way, this is on your reference table. 10 to the negative 8. All right, that's watts over meters squared times Kelvin to the 4th. Okay, well, before we even get started, we got to convert those to Kelvin. So I'm just going to come over here. I'm going to call this Fahrenheit to Kelvin. This is going to be a bit of a problem, so let's get started on that. If you look on your reference table, there's an area with your conversions to go from one to the other, so we're going to be using that. All right, so first thing we have to do is transfer this Fahrenheit to Celsius. So temperature Celsius is equal to temperature Fahrenheit minus 32 divided by 1.8. So TC is going to be equal to 91.4 degrees, skin temperature, minus 32 divided by 1.8. Now that's just a straightforward math problem. So the skin temperature is going to be 33 degrees Celsius. Now, to convert Celsius, we need to add 273. So, to get temperature Kelvin is temperature Celsius plus 273. So, 33 plus 273. And when we're all done, we're going to get 306 degrees Kelvin. And that's going to be our skin temperature, which is temperature 2. Do the same exact thing to figure out temperature 1, and all right, instead of you going through everything with me, I just did it again. There's the formula, same steps. So we have our TK for Kelvin, and it's actually number 1. That's our Kelvin for number 1, our Kelvin for number 2. Let's start solving some problems. Okay. Next, we're going to be looking at our formulas. Okay, see which formulas we're going to be using. We're going to be using the rate of heat transfer net gain. All right, we got Stefan's constant, we got our area, we got our temperature change, right, and we're going to be using this guy up here also, the change of thermal energy over time. So let's write those down. Okay, what we're looking for, we are looking for P, which is the rate of energy transfer. And we're looking for Q, which is the energy that's getting transferred into the room. So we want the rate of how fast it leaves the person and gets in the room, and we want to know how much is going to be transferred total. All right, let's move on. This one we know, so P is equal to the change in our energy over a little bit of time. Let's solve for Q though. Solve for Q, and that's going to give us change in Q is equal to the P times that. Okay? We also need the P net. That's going to be, that was bad, Stefan's constant, the area, and the emulsivity, and that's going to be multiplied by the temperature change. So we need T2 to the fourth minus T1 to the fourth, and we're going to have to solve for all of this. So let's put in our Kelvins. Let's solve for this part first. All right, so we're going to solve for the T2 first. All right, so T2 to the fourth minus T1 to the fourth. All right, since we know those numbers, we can work with that first. So we have 306 Kelvin to the fourth power minus 291.33 Kelvin to the fourth power. This is where the Desmos calculator can come in handy. Multiply that out. We get 1.564 10 to the ninth power Kelvin to the fourth power. Okay, so that number we need to put in our back pocket as we move on to the next step. All right, let's put down our P net. So we'll just come over here. So here's our P net formula. Let's do some substitutions. So P net is going to equal Stefan's constant, 5.6696 times 110 to the negative eighth. That's going to be watts over meters squared, Kelvin to the fourth. All right, that's going to get multiplied by 1.3 meters squared. That's our area times our emissivity, which is 0.9. So we got 0.9. And that's going to get multiplied by the number we just got, which is 1.564 times 10. Oh boy. 9th K4. We're running out of room. Anyway, so move all that over. All right, we're going to move all that over. First thing I'll do is I'll just combine those two. So we'll just shrink everything down. All right, 5.6696 times 10 to the negative eighth watts over meters squared Kelvin to the fourth times. Multiply those together, and we get 1.1817, and then we have the number over here, which is our temperature, 564 Kelvin to the fourth. Now we got a little more room. All right, so multiply out this formula and do some crossing out. All right, if you notice, we got Kelvin to the fourth. You can cross out Kelvin to the fourth. We have, oh, I forgot my meters squared. We got meters squared there. So that's going to get crossed out, meters squared there and there. And that's going to leave us with our watts. going to leave us with our watts. So if you have a Desmos calculator right here, you can see on the left, I entered all that information in, that whole formula. You can type in the whole formula. You can probably do it in a graphing calculator too, and then it gives us an answer of 104.98. So our P net is going to equal 104.985 watts. All right, here's our watts right there. That gets brought down. So that's going to be our P net. So that's how many watts of power the person is, gave off over the time. But we want to know the how much thermal energy that is. So that's watts. We want to turn it into some joules. So we're going to do our Q formula, P, and then how much time elapsed. So Q is going to equal to 104.985 watts times, and our time is 900 seconds. All right, multiply that together, and we're going to get 94,486 joules. So that's how much heat, or joules, that's how much joules the body puts off just sitting there for 15 minutes. All right, remember, 1 joule is equal to lifting an apple about a meter. Okay, there you go. It's a big problem.